Welcome everybody. Let's talk about limiting reactant stoichiometry problems today. So when you do a chemical reaction, more often than not, you don't have exactly the right amount of each chemical in the beaker or flask or your body that you need. Usually you have something left over and something that's going to run out and limit the amount of product that you can make. And that's what a limiting reactant stoichiometry problem aims to determine. What runs out, what's left over, and how much did you make? So the limiting reactant is the chemical that runs out first and therefore dictates how much product you can make. And the excess reactant is what you have left over when you're done. So I'm going to start us off with a relatively simple problem, and I want to focus on a BCA table where we already have things in moles. Limiting reactant problems are where BCA tables are priceless. They really summarize what's going on and make it so much easier to decide what limiting and excess reactants are and how much of the products you're going to form. So in this reaction, you have aluminum hydroxide, which is found in many antacids, reacting with hydrochloric acid, which is stomach acid. So if you take something like Rolaids, there's a chance this is the reaction that's going on inside your stomach. And the products of this reaction are aluminum chloride and water. Now, when you look at this, I have added 0.4 moles of aluminum hydroxide and 0.6 moles of HCl. First gut reaction, less aluminum hydroxide must run out first. But when you go back and take a look at the coefficients in your balanced chemical equation, you'll notice that it takes 3 times as much hydrochloric acid to carry out this reaction than aluminum hydroxide. So actually, you're going to run out of the hydrochloric acid first, because it would take 1.2 moles of HCl to use up all of the aluminum hydroxide that you've added. So that's going to be our limiting reactant. The chemical that you're going to have left over is going to be aluminum hydroxide, and this is our excess reactant. Now, I want to finish the BCA table and point out a couple of things. As I go to start it, use up all of your limiting reactant. So I'm going to fill this out, and we'll come back in just a second. Okay, so I used up all of the HCl, and then I did a proportion or conversion factor. You could also do this in dimensional analysis to figure out how much aluminum hydroxide would react with all 0.6 moles of HCl. I found that was 0.2 moles. Put that into my change line, because on the change line, the amounts of chemicals need to reflect the mole ratios, because that's where the reaction is happening. And I find that I've got 0.2 moles of aluminum hydroxide left over. And so when you look at this, you'll see that your limiting reactant, there's none left over. But for the aluminum hydroxide, my excess reactant, there does still remain some. And of course, I can use stoichiometry to complete the rest of this BCA table to figure out how much of the products I'm going to form as well. So I've completed my BCA table now, and I will make 0.2 moles of aluminum chloride and 0.6 moles of H2O, because once I've made that much, I'm out of HCl and the reaction must stop because I have no more reactants to use up. Let's take a look at one more example. And on this next example, we're going to do a full stoichiometry problem. So going from masses into the BCA table in moles and then out to masses on the other side, so you can see that whole process. Okay, I'm on antacids today. Another common antacid is Alka-Seltzer. It's the tablets you drop in the water and they fizz, and then you drink the remaining liquid. So what's actually making that fizz is the reaction between sodium bicarbonate and citric acid. And so if I had 1 gram of sodium bicarbonate and 1 gram of citric acid, the question is which of those would be limiting, which would be excess, and how much of any products would I make? Now, it's a stoichiometry problem. You have to start with a balanced chemical equation. And so I have this down here. I have 3 moles of sodium hydrogen carbonate. That is sodium bicarbonate, reacting with 1 mole of the citric acid, which has the formula H3C6H5O7. And I'll make 3 moles of carbon dioxide, 3 moles of water, and 1 mole of the sodium acetate. First thing we have to do, you cannot just look at grams. The limiting reactant in stoichiometry is about the number of moles. So we're going to start by converting all of our grams into moles. So we're talking about the same number of particles for these chemicals. So I've taken and used the molar masses to convert grams to moles for each of these. And now we can see we don't have the same number of moles since their molar masses were different. By inspection, I can tell that I'm going to run out of the sodium bicarbonate first, because I need 3 times as many moles of that as I do of the citric acid, and I don't have 3 times as much. So that's going to make the sodium bicarbonate my limiting reactant, and the citric acid, my excess reactant. So in order to complete this BCA table, I'm going to use up all of the limiting reactant and then use those mole ratios to determine how much of the other reactant is used up and how much of the products are going to form. Okay, so I use the 1 to 3 mole ratio to figure out the moles of the citric acid that were going to be used up. And that is 0.00397. And that leaves 0.00123 moles, which is a confirmation that that is indeed my excess reactant. And then I also looked at my mole ratios, although I didn't show all the conversions, for CO2, H2O, and then the sodium citrate, that Na3C6H5O7, to see how much of those would form. And since I started with none, because they are products, how much of those were going to be left over at the end. And so at this point in time, I've identified limiting and excess, and I have the amount of moles of everything that's going to remain, but realistically, grams are much more useful. So the last thing I'm going to do is, using the amounts of everything I have after the reaction, I'm going to convert that into grams. For every one of those chemicals, you're going to do a conversion problem using molar mass. So that's what's next. Okay, so I just did 4 conversion problems. It turns out that when this reaction is done, you have 0.236 grams of the citric acid remaining. You've made 0.524 grams of carbon dioxide, 0.214 grams of water, and 1.02 grams of sodium acetate. It is worth pointing out that we began with 2 grams of starting materials, and if you add up all of these masses, you've ended with 2 grams of products. The law of conservation of mass holds true, and this stoichiometry problem just illustrates how much of everything and allows you to predict what are you going to have when you're done. That CO2 is going to have gone off into the air, and left in that beaker is going to be the water, the sodium citrate, and the leftover citric acid. So when you go to work a limiting reactant problem, you of course have to start with a balanced chemical equation. That hasn't changed. And then from there, you're going to convert any values that are in grams into moles and start filling out your BCA table. That part hasn't changed. Then you're going to look and try to decide which of the reactants is the limiting reactant. If you can do it by inspection, awesome. If not, guess and check. Plug one in, try it, see how it goes. Once you've identified your limiting reactant, you're going to complete the rest of that BCA table. And that is going to allow you to figure out how much of the excess reactant remains, as well as how many of the products you have formed on the other side in terms of moles, which you can then convert to grams if you are asked to do so. Have fun with them.